In this video, I'll introduce the concept of an integral and a process called integration. As with derivatives, I'm not going to provide a rigorous mathematical definition of integration here, but I will give you a general idea of what an integral is. Integrals are important in engineering since energy storage is the result of an integration. In a sense, integrals are the opposite of a derivative. They convert the rate of change of a value to the value itself. If you integrate the derivative of a function, you'll end up with something very close to the original function, with the possible exception of an undefined constant. The derivative of a function is just the rate at which the function changes with respect to its independent variable. If you plot the function, the derivative will be the slope of the function at any point. The equation for the derivative of a function is always tangent to the curve representing the function itself. An integral is just the opposite or inverse of a derivative, so that integration will, in a sense, undo a derivative. That is, if I take the derivative of a function and then integrate that derivative, I'll end up with something that's close to the original function. It turns out that the integral of a function is just the area under the curve describing the function. With that in mind, let's introduce some terminology relative to integrals. Suppose we have a function f of x that we want to integrate. Since the integral is the area under the function, this depends on what section of the function we want to integrate. Integrals are specified between 2 points, called the lower and upper limits of integration. So if I integrate this function between a and b, I'm finding this area. Notation-wise, the integral I of a section of the curve between points A and B is expressed this way. This symbol represents integration. The lower limit of integration is down here, and the upper limit is above the integral sign. The function to be integrated, f of x, appears between the integral sign and this dx. The dx indicates that we're integrating with respect to the variable x. This is read as integral from a to b of f of x with respect to x. One reason this is important is that engineers are often interested in how a system's energy changes with time. Energy is always the result of an integration. So if you're watching a frying pan's temperature change as you apply heat to it, or if you notice your car's velocity change as you apply the brakes, you're observing an integration. The fundamental equations for dynamic engineering systems dictate the rate at which energy can change. For example, Newton's third law says that the sum of the forces applied to a mass is equal to the mass times the acceleration. Acceleration is the rate of velocity change with time. So, Newton's third law governs the rate of change of the velocity of a mass. This is just the ratio of the applied force to the mass itself. To determine the energy in the mass, we need to undo this differentiation process. By integrating this derivative, we can recover the mass's velocity, which gives us the kinetic energy in the mass. Notice that this is actually a change in velocity between 2 times, a and b. In order to determine the actual velocity, we need to know the velocity of the mass at time a when we begin the integration process. That's what I meant earlier when I said that the integration undoes a differentiation process, with the possible exception of an unknown constant. This unknown constant is called an integration constant, and it can't be determined from the integration itself. You need what is called an initial condition. As an example of an integration, if we drop a rock at the Earth's surface, it'll accelerate downward at an approximately constant rate, 9.8 meters per second. So this is a plot of the rock's acceleration. We've already seen that acceleration is the rate of change or the derivative of velocity, so velocity must be the integral of acceleration. So the area under the acceleration curve will give us the rock's velocity. But first, we need an initial velocity at time equal to 0. If we assume that the rock is initially at rest, this initial velocity will be 0. So this is our initial condition, or the integration constant. Since velocity is the integral of acceleration, the change in velocity between 2 points is just the area under the acceleration curve between those points. So the velocity at a time t1 is the initial velocity, 0, plus the area under the acceleration curve between times 0 and t1. This area is just the area of a rectangle with height 9.8 and base t1. So the velocity at time t1 is 9.8 times t1. Likewise, the change in velocity of the rock between time t1 and t2 will be the area under the acceleration curve between t1 and t2. The velocity of the rock at t2 is 9.8 times t1 plus 9.8 times t1 minus t2, which is just 9.8 times t2. If we do this for every value of time and plot the resulting velocity as a function of time, we get a straight line. Velocity increases linearly, and the slope is 9.8 meters per second. This is the same result we had in the video on derivatives, which is a good thing. Now let's take a look at what the position of the rock is as a function of time. From the previous slide and basic intuition, we found that the velocity increases linearly. Since velocity is the rate of change of position, if we integrate velocity, we should get the rock's position. As before, I'm going to need an initial condition. I'm going to assume that the rock's initial position is at 0. The area under the velocity curve at time t1 is going to be this little triangle. The triangle has a base t1 and a height v1, which is the velocity at time t1. The area of a triangle is 1/2 times its base times its height, so the area is 1/2 times t1 times v1. This is then the position of the rock at time t1. Likewise, the area under the velocity curve at time t2 is 1/2 of t2 times v2, where v2 is the rock's velocity at time t2. This gives the rock's position at time t2. So this is approximately the rock's position as a function of time. Notice that the rock's position is changing more and more rapidly as time increases. These are pretty simple examples, but the general idea applies to more complex situations. Most functions engineers work with aren't this simple, but an approach similar to this can let us determine an area under a curve that has some weird and arbitrary shape. That concludes my introduction to the concept of integration and its relationship to the area under a curve. The examples I did in this video were pretty simple, but this basic approach can apply to more complex problems. Using numerical techniques for determining integrals of arbitrary functions isn't terribly difficult, but we will rely on a computer's ability to rapidly perform a lot of simple calculations. In the next video, I'll explain how to integrate an arbitrary function numerically.